Hello, we are Group 8, Machine Learning and Evaluating Technical Documentation. We are working with NetApp. NetApp is a company that specializes in creating innovative products for data management and storage and cloud data services. They are interested to determine how effective different NetApp-specific technical documentation is at conveying different technical specifications.
The very first thing we did was scrape 13 features from the document, which were then used to calculate 18 different readability scores. We used dimensionality methods such as PCA and UMAP, which are linear and nonlinear respectively. Then we found a sparsity measure of the documents represented as a vector encoding the conditional distribution of an n-gram model. And finally, we used deep learning methods to predict the readability score with document embeddings in a moderately high dimensional vector space using labels generated from the UMAP dimensionality reduction. In the table that you see here, you can see various features that we extracted, such as total words, sentences, characters, etc., as well as all the readability scores that we calculated. We did not calculate KDRI because it accounted for the number of foreign words in a document, and all of our documentation was in English. We used the PCA dimensionality reduction method as a nonlinear way of reducing our data. We did this because the readability scores had a lot of overlapping features and we wanted to reduce the redundancy and optimize for computation and memory. So we were able to bring down our data into two principal components, which accounted for about 90.5% of the original variance in the scores. We also used UMAP dimensionality reduction to visualize the nonlinear aspects of the data.
Moving on to distributional sparsity, the idea is that given a sequence of words, W1 through Wn, we want to predict the next word as accurately as possible. So we can do this using n-gram models, which goes through the documents and stores the possible next words by going through a list. So as you can see over here, you said an active IQ would be the next word in this documentation. A high count of next word indicates that there's a lot of possibilities of next words, meaning that it's harder to predict and therefore you have a lower readability score. So we specifically measured this with the distributional sparsity of the documentation vector. In the neural network, what we basically did is we took the document and we represented it as a vector using something called a word-to-vec embedding. And then with this, we trained a neural net with comparing it against the labels of the dimensionality reduced from UMAP. So, and as you can see below in the figure, the deviation around the training and testing errors indicates that document and UMAP embeddings may be uncorrelated, leading to difficulties of the neural net finding patterns.
Here we have two different examples of documentation readability scores. Towards the left, we have a document that has a higher sparsity, which indicates lower readability and hence is harder to read. Towards the right, we have a document that has lower sparsity, which indicates higher readability and hence is easier to read. In conclusion, using a combination of established readability scores gives an accurate measure in technical documents. We can work on the interpretability of these algorithms. The sparsity of the word distribution from the corpus are left skewed, indicating that few documents are extremely easy to read, while most of the documents roughly follow a normal distribution. Thank you.